First of all, I would like to thank Dr. Zhu for his kind invitation, and also from Dr. Tsai for kind invitation. Today, I'm going to talk about some topics in covalent organic frameworks. I will concentrate on two issues, namely the linkage chemistry and the host guest chemistry. Basically, I guess all you guys should know the concept about and the research here about the covalent organic frameworks. It has been recently received a lot of attention because this kind of crystalline porous polymers, basically, they are composed from organic components that they are constructed with from the organic small molecules, which are covalently linked together. This kind of new materials featured with crystallinity, porosity, and extended structure. The first report on this research came from Professor Omarjaki, who report their the first contribution in 2005. Basically, they were using the boric acid as a building block. They put them, construct them together with a covalent boron oxygen bond. So it's our first report to get the crystalline organic polymers, and implements should be, first of all, that means you can create the periodic structure with strong covalent bonds. And the second implication would be this kind of new materials could be the potential platform for many many applications you can imagine. For example, from absorption, recognition, catalysis, photocatalysis, and so on and so on. And but at that time, I would say that the biggest problems in the new research here would be, first of all, how could we create the new and the stable structures, and is there possible that you can develop a different kind of linkage and also different kind of structures so as to meet the demands for a variety of applications. So in that case, we are working in this area for a long time, and we focus on the basic. We focus on try to answer the basic questions of in the research area of cost. For example, how to create the different kind of linkers so as to reach the demands for crystallinity, stability, and functionality. And most of all, we're trying to integrate them together, because sometimes if you get the good crystallinity, but still you cannot reach the high stability. And if you can meet the demands for both crystallinity and stability, but this kind of materials could not reach a variety of functionality. So basically, we try to develop a different kind of linkage chemistry and try to reach the demand to integrate all this crystallinity, stability, and functionality together. So if we want to do this, we have to put a lot of effort on the design of the building blocks, and also on the design of the organic chemistry which can be applicable to the linkage construction in the COFs. And the next question would be, how could we know we have successfully construct the linkage? In that case, of course, you can use different kind of characterization approach. For example, you can use the X-ray, powder X-ray diffraction, and you can use the porosity. It's got the isotherm measurements, nitrogen absorption or gas absorption or measurement, and so on and so on. But if you want to look at the details to check whether you have successfully constructed your linkage, you have to be very careful. For example, we are for a long time we are trying to to apply the solid state NMR to characterize not only the linkage chemistry but also the porosity and also the host gas chemistry and the mechanisms involved in the for the COF applications. So in the first part, I would like to share with you our research or our efforts on the construction of the on the linkage with high stability, functionality, and the crystallinity, and we try to check all the details with the success of your construction on the linkage by different kind of techniques. But today I focus mainly on the solid state NMR. So we start at actually in about 10 years ago, we constructed the so-called the first two-dimensional image-linked COFs. We were using these two different building blocks, and we connect these building blocks together with the image linkage with a so-called hydrothermal synthesis. And in this research, is not only the stable image linked COFs can be built up. Also, it's opened up a new possibility to apply this kind of COFs for diverse application. For example, for their application in heterogeneous catalysis. And next would be, if we can build the COFs with image linkage, is that possible? We go further to make the linkage either stronger or either with integrated with further functionality. In that case, our first effort is construction of the silent COF. Basically, we use a strategy called killing two birds with one stone. We designed these two different kinds of monomers, and we use a one-step construction to successfully construct the silent linked COFs, in which the silent linkage has been constructed in one step. And the feature of this silent COF would be the integrate the stability of the linkage and the potential functionality as a silent motif into one COF. And in that case, you can use for example, the post modification to impregnate different kinds of metal ions in this silent sites, and also you can do the catalysis even with the metal contained silent COF, or you even use the silent COFs themselves. So the question would be, how could you know you can you have successfully get this silent linkage? So we can use carbon 13 CP mass NMR technique to check the successful connection of this silent linkage. As you can see in this spectrum, all the carbons in this silent moieties can be separately assigned with different carbon 13 peaks, and also the NMR signal at 188, which is corresponding to the terminal aldehyde groups, is an indicator as to evaluate the periodicity of your sample. And as I just mentioned, we moved from the fragile boron oxygen bond to the more stronger, for example, the imine bond and silent bond. And that the further question would be, is that possible to move further to get a stronger linkage? That means you need still to reinforce or strengthen this we call the mortise and the tenon joints. And how to reach this this issue? Actually, basically, there's a lot of inspiration from organic chemistry can do a lot, and we can benefit from their inspiration. For example, the so-called cascade reactions could possibly reach this goal. In that case, before we are using this these two building blocks to connect to get the imide bond linkage. But if you install a hydroxy group in the adjacent site, you could possibly get benzyl oxyl group as a ring linkage. In that case, the stability of this linkage can be further increased. So, is that possible to use this chemistry to get a strong to get those ultra stable linked COFs? And after many times of our to screen the construction conditions, we did we successfully constructed the so-called benzyl oxyl linked COFs, and basically we were using these two different kind of building blocks, and we use the cascade reaction as I addressed just now, and we get this strong linkage. In that case, if you compare this the stability of this link, the benzyl oxyl linkage with amine or the silane linkage, this kind of COFs can remain their high stability even in strong solids or basic conditions. And as a result, you can use this this COF to do the photocatalysis. The recyclability is unprecedentedly high because due to the high stability of their framework. So the question would be: is that possible to identify the formation of the benzyl oxygen zone? So in that case, if you are dealing with a small molecules, so quite easy to get this information, because you can check whether you have this proton or not with its amine ring. But in that case, if you want to check the information with extended frameworks, you have to use a so-called carbon-13 NQS NMR technique. In that technique, actually you differentiate the quaternary carbons with different non-quaternary carbons. In that case, all the non-quaternary carbons would be the signal's intensity would be suppressed, and only the quaternary carbons can survive. So in that case, you can identify the chemical shift of the 163 as the quaternary carbons, which is strong evidence for the formation of this benzyl oxygen ring. So in that case, we still want to explore different methods to integrate the crystallinity and stability and most important, the functionality into one COF sample. In that case, we developed the so-called multi-component strategy to achieve this goal. Basically, in the research we contribute before, our monomers are constructed are derived from two parts. The first one probably is for the functional part, and the next one would be the structure monomers. Is that possible? We can use multi-component monomers. In that case, the task to construct the COFs can be divided or can be separated with more components, so as to minimize the effort for the design and the synthesis of the monomers from the beginning. For example, in this case, we can use the so-called DR reaction. We can put these three components together and construct this imidazole linked COFs in one step. So in that case, we actually achieved a new level of complexity, and also with the precise construction of this COFs with both stability and the crystallinity. And furthermore, if we want to integrate this ultra stability with the functionality into one COF, we should explore or look for different the new new chemistry, because so far, if you you can improve your stability, or you can improve your functionality separately, but it's very hard to integrate both stability, or if we want the ultra stability together with the functionality together. So we exploited the isocyanide chemistry, and we applied this also a multi-component strategy into the formation of the COF the COF systems. In that case, we can design different 3 components which can be constructed in one step into this multi-component functionalized structure. In that case, we are not only achieve the stability of the structures, but also the diversity of the functionality can be introduced from beginning from this building block. So in that case, we still face to a problem in how to identify the successful construction of the linkage. In that case, we can combine the solid-state NMR techniques together with so-called selective isotope labeling experiments. For example, we can M15 label this starting material, and we can use a solid-state NMR to monitor the transformation of this building blocks into the COF, so as to identify the successful connection of the linkage we expected. For example, this is the M15 carbon M15 CP mass spectra for this for the COF, the imidazole COF to be constructed with the multi-component strategy. And all the above mentioned contributions are mostly focused on the development of the linkage chemistry, so as to get the COFs with both stability and we tried, and also the crystallinity. But is that possible? We can move forward to not only to get the polycrystalline COFs, instead we can harvest the single crystalline COF. In that case, we developed the so-called the modulator strategy. Basically, we alerted the construction strategy from the imine formation to the imine exchange. In detail, we can, in the presence of the certain amount of the aniline as a modulator, we can modulate the formation process of this imine-linked COFs, and through which we can obtain the large size, high quantity single crystal COFs. And in that case, you can use the single crystal X-ray diffraction technique to directly get the crystalline structure at the molecular level, at the atomic level. For example, you can use the X-ray diffraction technique to directly get information about the topology of this LZU111, which features with the color topology. And in that case, you can use a different characterization technique to identify the quality of this single crystal COFs, for example, the LZU111. Like, as you can see, the resolution and the characterization data for this single crystal COFs is pretty good if you compare it with the data obtained from the powder samples and the polycrystalline samples, basically. So that's our efforts to further improve the crystallinity of the COFs. And is that possible? We can, as I mentioned, we can integrate all the stability, crystallinity, and functionality together in one system. I'm going to show you our recent contribution to this issue. Basically, we are developing the linkage chemistry from the imine-linked COFs to the single ring-linked COFs. And is that possible? We can get the gets a fused ring link coughs. In that case, basically we need to think about how to design the monomers and how to design the chemistry potentially involved. And basically the chemistry we try to develop to get to construct the fused ring link coughs is the key chemistry is the intramolecular 4+2 cycle addition. And you can first try with model systems. That means you can put these two small molecules and they can experience with the shift-based condensation and the intramolecular 4+2 cycle addition followed by the dehydrogen aromatization, and in that case you can get the fused ring, the so-called perennial pyridine this moiety. So this is that possible? This strategy can be transferred to the construction of the fused ring link coughs. After a lot of effort for screening the research the synthesized conditions, we do get successful constructions of fused ring coughs with a variety of the building blocks. We can get a different kind of fused ring link coughs with different topology. So, and now the next question still there. That's how could you prove the formation of your fused rings? In that case, we can compare the solid state NMR spectrum between the imine linkage and the fused ring linkage. So you can you do see the signals for this side chains has been transferred to this peronal rings. So in that case, you can see the formation of the peronal rings, but it's the key evidence is whether the formation of this quaternary carbon at the 148. But in that case, we do see the signal as 148 in your in this fused ring coughs, but this signal can be overlapped with different signals, and also this can be originated from other possibilities. So could you identify the pure formation of these quaternary carbons as the evidence for the formation of the fused ring? So in that case, we combine the selective carbon 13 labeling experiment. We start with the selective carbon 13 enriched monomers. We can monitor the transformation of this monomer to the fused ring coughs from the carbon 13 NMR spectrum. You do see the dominator signal as 148. So it's strong evidence for the formation of this fused ring. So the next question is, we do see the formation of this fused ring as the evidence to say we have a successful construction strategy. But how do we know the selectivities? That means is that from the same starting point, we could have different possibility, for example, to get imine linked coughs or the fused ring link or other different possibility. How could we know we get this get exclusively the formation of the fused ring? In that case, we should use a quantitatively NMR to in combination with the selective carbon 13 labeling experiments. So when you look at the results from the quantitative NMR, you do see the formation of this perennial pyridine. That means the fused ring as a percentage of 95% also. So if you calculate this is the selectivity from the 3 steps, so you can say the selectivity of each step would reach more higher than 97%. That means we do have this high selectivity, and that means we get almost the exclusive formation of the fused ring linkage in this technique. So I hope I finished the first part. I report you with different samples we constructed in the past 10 years or so. We start from the formation of the imine bond, and we move further, try to develop different linkage chemistry to integrate the stability, functionality, and the crystallinity together. We try to update different strategy from the organic chemistry to fit the dynamic covalent chemistry in the COF research, and we try to move the quality of the samples from the polycrystals to the single crystals, and we try to set the new standard to check not only to identify whether the formation we expected has been formed or not. We try to establish a quantitatively standard to measure what's quantitatively to evaluate the selectivity for this linkage chemistry. So the next topic would focus on the host gas chemistry of the COF. Basically, it focus on the applications, because the crystalline porous samples should get their unique use due to their structure uniqueness. In that case, we should understand the features of these COFs. For example, the crystalline structure, the organic components being linked as a framework, and most importantly, you get the pores which can host different gas samples, and for further you can do the chemistry inside the pores, and you get the transformation of the gas. So in that case, you should understand first of all the host gas chemistry, and also you can get to monitor or to evaluate the different property or even the transformation of the gas molecule. Anyhow, this is based the chemistry. The key scientific issues would be how could we identify or how do we evaluate the structure performance relationship. I would like to give you a couple examples of our research, and basically we have been using the COFs to achieve the catalysis, the heterogeneous catalysis, the photocatalysis, and so on and so on. But today I do not have time to report this example. I just show you some of the basic issues we try to attack with the host gas chemistry. This is an example we established that we try to make the diversity of the functionality of this COF from the side chains. So in that case, we can use this different functionalized COFs as a new platform to selectively recognize and also for recover the heavy metal ions as a gas. In that case, we can design and synthesize this COF LZU8. The structure feature of this LZU8 is that it has a stable framework, and also it has a functionalized side chain. The sulfur alpha functionalized side chain. In that case, this host can work as a new platform to absorb or recognize selectively the metal ions, for example, the mercury ions. So how could we identify this host gas chemistry between the mercury ions as a gas and the LZU8 as a host? First, we can measure and we can compare the CP mass carbon NMR spectra between the host and the host gas system. If you compare their spectra, you can see that all the other signals are are remaining the same, expect the signal at a 28 ppm signal has been low field shifted to 35 ppm after the inclusion of this gas molecule. If you remove this gas molecules, the gas is the mercury ions out, and you get back your carbon 13 MR spectrum. So in that case, you can identify, you can prove that you do see the interaction between the host and the guest by the change and the recovering of your MR spectrum. And also you can know that the mercury ions are selectively bonded to this size. That means it's close to the sulfur atoms, because only the adjacent carbon atoms has been influenced, which can be seen from the change of the carbon 13 MR signal. And also you can quantitatively evaluate the interaction, because it has been changed. The chemical shift change at about 7 ppm. And also, if you work with other gas, for example, the CD ions, and you do not see the chemical shift change. So from this example, you can not only identify the selective interaction between the mercury and the host, and also you can quantitatively evaluate the interaction by this carbon 13 MR. The next example would be how could we identify the structure change upon the gas inclusion. In that case, we discovered the dynamic behavior of one three-dimensional curve, and the feature of this three-dimensional curve will be upon the gas inclusion, the structure, the framework structure can be changed. So the basic question would be, how could we know the structure change upon the gas inclusion? In that case, we can use the xenon as a special gas, or as a monitor or the indicator. You can monitor the chemical shift change upon the inclusion of this xenon. In that case, you can use a so-called viral pressure xenon MR, and you do see the phase change from the contracted phase to the expanded phase upon the increase of your pressure. Or you can see this reversible change with a variable temperature xenon MR measurement as well. So, and also if you can use the single crystal structures as a platform to evaluate the mobility of the rotational features of certain molecules. In that case, we constructed the single crystal LZU 3006 as a non-interpenetrated, as a first example of the interpenetrated single crystal curve. In that case, you do see there's morphology, and also you can see the resolution of the MR spectrum get increased, and of course the porosity and indicates their high periodicity of the structure. And most importantly, you can selectively deuterate the proton with the benzene ring, and you can use a variable temperature deuterated deuterium MR to identify the rotation of the single molecules as a new platform to evaluate the property of the single molecules. And I will report you as an example to say what's the potential functionality for some coughs, which you can use the coughs as a host, but this host can identify the structure of the gas. Basically, this kind of technique is called the DMP. DMP techniques is basically this technique is recently applied as a new approach in the NMR research, and in that case, you should use radicals as a DMP agents. But the problem is if you blend your radicals with your target, which you want to get a structure, and it's very hard to get a homogeneous distribution of the radicals, and also you cannot control precisely of the concentration of radicals, because upon the measurement at low temperature conditions, you do get aggregation of your radicals, and also the mobility of the radicals can largely influence the signal enhancement during the measurement. So the key question is that possible we can fix the radicals into some certain framework, and also we can adjust the concentration of the radicals precisely. All these two demands can be fulfilled in one, for example, with the radiculation of your radicals into the Coff framework. In that case, you can use radical and their reduced form together with one building monomers to construct the radical reticulated Coff. In that case, the concentration of the radicals can be adjusted from the beginning with the ratio between the radical and their reduced form, and also the orientation of the radicals can be fixed, can be perfectly fixed, because it has been reticulated into the framework. It cannot be moved around. So in that case, we can use that. For example, use different characterization to identify the porosities, the crystallinity, and so on and so on. And also we can use the ESR to characterize the homogeneous distribution of these radicals. This X indicates the percentage of the radicals in different samples. For example, the 10 means that 10% of the radicals inside your inside your Coff system. And in that case, whether it can be used as an efficient DMP agent or not, we can test this with DMP DMP facilities. In that case, if that means if you measure with without the DMP condition, you barely see the signal. But if you work with the DMP condition, that means you put this Coff radical samples inside your system, and you can measure, you can get a very good signal in just 16 scans. This is the bottom is the corresponding M15 NMR spectrum. In that case, normally we could not, it's not possible to get the M15 NMR spectrum with the non-enriched samples. But in that case, if you work with a DMP condition, you do see the very good spectrum. That means DMP efficiency is pretty high with this radical impregnated Coff samples. So we can evaluate also the efficiency of this this series of this radical reticulated Coffs as a DMP agent. You can quantitatively evaluate the efficiency. That means you with sample with 20% of the radical inside the sample, you do have the highest proton NMR DMP NMR enhancement, and also you get also the carbon-13 DMP enhancement. And what's the next functionality for this radical enhanced Coff? So you can use this one to test the signal of your gas. For example, you can test the sample with test the signal with the gas sample, and you do see the high signal intensity of this gas sample. And if you work with even with a high field, you do see the very good signal with to test to get information of the gas samples. And now we are working with with how to synthesize, for example, the radicals and also the radiculated coughs in large quantities, so we can push forward to use this radical impregnated coughs as a new DMP-rich agents for practical applications. So I would like to make a short summary. I try to convince you from in this talk that we try to put our focus on the basic questions in the research area of coughs, and mainly focus on the development of the linkage chemistry, so as to integrate the crystallinity, stability, and functionality into this cough system, so as to give a platform with this kind of new materials to reach different applications. And in that case, we should know or identify their structure characterization performance relationship. In that case, we use a solid state NMR in combination with selective isotope enriched experiments. We try to identify the quantitatively identify the interaction between the host and the guest, and also we try to explore the unique applications of this coughs as new materials. So all the work have been done from my co-workers, my students, and without their continuous efforts, I should not have any possibility to present this result to you. And also, I would like to thank all my collaborators, and also I would like to thank all the findings from the NSFC, MOE, and 111 project. And finally, I would like to thank you all for your kind attention. Thank you.
So thank you for your fantastic talk, Professor Wang. I enjoyed it a lot. So now we have some questions from online audience. So the first one is from Akapraba Jiri. So the question is what is the role of modulator to improve crystallinity? How a modulator improves the reversibility? Will it reduce the energy barrier for cough formation? Yeah, this is the question. Yeah, I think it's related to that multi-component formation of a cough, right?
Yes.
Yeah. The next one.
Oh, that's too much.
Maybe.
So basically, when you are applying the aniline as a modulator, you actually change the reaction events from the imine information to this called imine exchange. That means this kind of a series reaction can be alternated, or the imine exchange reaction dominated the whole events instead of the imine formation, because the imine formation is a reversible formation, but the reversibility of the imine formation is not so high. That means in that case, the forward reaction is faster than the backward formation. In that case, it could be similar to the process we get single crystals from the small molecule systems. If you can adjust the ratio between the condensation and the recombination of this process, you do control the crystallization process. In that case, if you put your aniline as a modulator, actually you alerted the kinetics of the forward reaction and the backward formation. So in that case, actually you mimic the conditions to get single crystals of the small molecules. Yeah.
Okay. So thank you. There is another question. Maybe it's similar in this page. So Dr. Hasil from Pakistan, the question is, yeah, he says, thank you for your nice talk. How the addition of a modulator can improve crystallinity? It seems like it can block your monomers. Yeah.
Yes, basically it interrupts the formal reaction between the aldehyde monomer and the imine monomers. So actually as an adjuster or interrupter, basically it's changed the ratio between the forward reaction and the backward reaction. So that means you get this this dynamic covalent chemistry more reversible. It's a function of this modulator, and basically it mimics the reaction to the conditions for growing the single crystal small molecules.
Yeah.
Condensation resolution. Oh, what's it called? Dissolution. Sorry, condensation dissolution. This is a condensation dissolution. So in that case, in the presence of this aniline, they change the relative kinetics between the dissolution, the condensation and dissolution. Well, called what is it? Dissociation. Yeah.
So here's another question. So I think it's many people may ask you this question. So here, so the questioner is Enoch S. So sometime when we check powder XRD, we will be getting amorphous peak signal. What's your suggestion to improve the crystallinity and avoid amorphous nature? Amorphous nature. Yeah. So
okay, that's basically yeah.
Question.
Basically, there are two aspects. The first aspect is based on your understanding of this so-called dynamic covalent chemistry. If you get more insight into the DCC chemistry, you can better understand the conditions which can be applicable to fit the DCC chemistry. For example, the modulating story would be one of the examples. The first of all could be like you need know-how. This know-how, there's no secrets there. You just need to try. It's like if you want to get your single crystals of with a small molecule, you still need to change a lot of conditions. For example, with the concentration, with the solvents, with your temperature, with even with very subtle difference in your crystallization process. And these two aspects has to be done simultaneously. And in our case, although we report the successful results, but actually my students have suffered with a lot of unsuccessful data as well. So, but from that they can just try to get the right way to get the samples with high crystallinity. It's a kind of try plus understanding. First, there's no rule, general rule.
Yeah, thank you. So good message for our audience. And I think this is a common general question because since the discovery of cough in 2005 or 6, it had become a hot topic, and actually get the single crystal of cough is a dream. Maybe it's a dream. I don't know. It should be a dream of the researchers in this field. So I ask for our audience, maybe, can you tell us some story about this discovery or this achievement? How can you get this breakthrough? Yeah, and is there any story you can share with us?
So first of all, I would like to say it's a kind of serendipity, and it's kind of luck, and of course, it's most importantly, it's kind of a great contribution to my students, my co-workers, and that's a lot of event put together. The first of all would be, actually from very beginning, we raised this question in our research group, and I asked whether it's that possible to get the single crystals. I believe many people would ask this question as well, and it's about 2011 also. I think about that time. And of course, at the time we do not have in-depth understanding of the DCC chemistry by that time. We still work on, for example, the construction of imine-based coughs, and together with the exploration of their different applications with this imine-based cough. For example, as for the application as a heterogeneous catalysis for recognition, and so on and so on. But at that time, we moved forward to try to construct the 3D coughs instead of the 2D coughs based on the imine linkage. And one of my best students is Miss Thieme Ma, who's a talented student. She came to my group I think 2011 or around that time, and she's task is to create or to construct the 3D coughs, and in that case, she did a lot of efforts and work on the construction of new topology for them with we call it 4+4 strategy. That means you use two tetragonal structured monomers try to construct with new topology. That's origination of this called the LZU111. In that case, she was able to grow large-sized crystals, of course, but at that time, it's not a single crystal in that case. At that time, with the chance I visited USA for research, and that's how I met Dr. Sean Yin. He's an expert in crystallization and structure identification as well. And in that case, he visited us back, and he looked at our samples, and he gave a lot of instructions to how to grow the single crystals in principle. And after a long time of efforts, I think Dr. Thieme did get this. Find a way to get single crystals. That means with with the modulator strategy. This is about the story about the growth of the single crystals. And of course, later on, we worked together with Junliang Xun and Professor Omar Yagi, try to get the different, try to get the structures done, and also try to grow a series of these single crystals. But the first one is the first effort is LZU111. We get the success, and we grow the other, for example, COF 300 and other systems with this the similar strategy. Yeah, I think that's probably the most of them.
Here is
yeah,
great. So we can maybe our young researchers, including me, maybe we can learn a lot from this success, collaboration efforts, a long time So maybe the time is limited, but I want to hear is the last question. Yeah, how to grow single crystal of 2D COFs? How to grow single crystal of 2D COFs? Well, here's no, sorry. So you have successfully get a single crystal of 2D COFs. So how to get the single crystal of 3D COF? Yeah, it's possible, and are you trying to do it? Yeah, here's the question. It's from
basically for the growth of the 2D COFs. I think Professor Dihito has made great achievements in this area. In my group, to be honest, we do not have much effort on this 2D COFs. We are mostly we are focusing on the growth of the 3D COFs, and I think Professor Dihito and other groups have already applied different strategy. For example, the seed strategy, the modulator strategy, and also different strategy try to harvest the single crystal 2-dimensional COFs, and I believe they already get the big achievement as well. Yeah, but we are not doing that.
Okay, thank you, Professor Wang, for your wonderful talk, and take time and to answer the questions from me and from our online audience. Yeah, thank you very much.
Thank you.
And here is any other questions. I will share this question with you later and with our office, editorial office. Okay.
Sure.
Yeah. Thank you.
Okay.
Yeah.
Thank you.